Let's go ahead and start now then. My name is Håkon Hamer. I'm the Executive Officer of the Nordic Society of Human Genetics and Precision Medicine. Welcome to the second webinar of our 2021 season. And I hope everyone is surviving well and doing well as COVID continues to increase. The webinar today will be by Søren Brunak, studying health and disease throughout the lifespan, with panelists Lily Milani, Paul Njølstad, and Kari Stefansson. The Society has, for those of you who are new here, has been up and running since 2018, and we've held several meetings that were significant in getting the Nordic community together. We've been engaging with other groups and other stakeholders, and we've been building an information platform about Nordic research and policy. And just I encourage you to visit our website, join and subscribe to our newsletter to keep up with the latest news in the Nordic region about science and science policy. And finally, this year we will at least have one conference, which will most likely be a virtual meeting on Nordic response to COVID-19. And our biennial meeting, which has been postponed, is still pending. We will have to decide at some point this year, depending on how the pandemic goes, what happens with the biennial meeting. And we have some upcoming webinars. Samali Ripati will be our next speaker, and we'll send more details out about that. That is the end of my slides. And I just make a few announcements. The panelists are all muted and pictures are on their cameras are off. We will be having questions after the talk by Søren Brunak. And so I encourage you to put in your questions at the bottom of your screen. You can actually upvote questions, ones that you find particularly interesting. We'll have some discussion with Søren, with the audience after his talk, and then after that we'll move into the panel discussion. I will now turn it over to Søren.
So first of all, thank you for having me. I will be talking about phenotypes, and especially temporal phenotypes, using lots of data from Denmark. And the whole idea talking about longitudinal phenotypes in this way is, of course, that we then have something to link to molecular level biomarkers. I will not talk much about that, mainly about how we construct these longitudinal phenotypes. So we all know that during the life course, we get diseases one after another, and of course also co-occurring diseases. You might start out reasonably clean in the middle of this diagram, and then you get the yellow disease, and then you get the green disease on top, and the blue. And all this disease journey is, of course, influenced by genetics. It's also influenced by somatic mutations arising, and of course also the exposure in many ways. And in the exposure we will also, of course, include treatment, and I will talk a bit about that in this talk. But what is the systematics in these multimorbidity journeys, how do we actually compute these longitudinal phenotypes that we then can compare to genetics and other biomarker data sets? Because that is, of course, what is interesting, finding disease progression SNPs, for example, that will drive the speed of disease progression. Some diseases, at least in some people, will progress very slowly. In other people, they will progress very fast. And being able to discriminate between fast and slow progressors is, of course, a key goal, and in a lot of ongoing work. But we can also look at this across diseases and look at it from a multimorbidity viewpoint, and this is what I in particular will deal with. It's quite nice, of course, that many of the biomarker data sets that are becoming available, they are sort of also linking to all diseases in one go. At least, for example, with the whole genome, there might be many genetic markers for a lot of diseases, but there are also, of course, also so-called non-genetic diseases if they exist. But at least these diseases also, in many cases, very linked to genetics when it comes to their treatment. So genome data is one type of data, but of course also proteomics data will also be useful in many different disease contexts. So this development where biomarkers have gone sort of disease wide, disease spectrum wide, is of course something that also is a motivation for the kind of work that I will describe. So what is a disease, and how do you use ontologies to describe diseases? This is something that has been going on for more than 100 years, and of course something that develops in healthcare. The WHO International Classification of Disease model has been used for many years. Started out as a course of the causes of death classification, but now much more fine-grained. But actually, these guys who started out in 1893 with this, they also highlighted that this is something that evolves, and whenever you publish a new ICD version, it will essentially be obsolete when it is published, because knowledge develops. So here's how ICD in terms of the number of diagnosis codes have evolved. There are many, you see, from a few hundreds and then to the 10th of thousands, and this is of course the official WHO version. And in many countries, this has been expanded. And you see to the right, we will soon roll out ICD 11 with 55,000 unique codes for injuries and diseases and causes of death. So all this business of how we actually describe diseases longitudinally is something that, of course, also involves. And eventually, what we are after is obviously a mechanistic disease classification, not just something that is based on symptoms that ICD in many ways is. We would like to classify the diseases after their mechanistic properties and use omics data for that. But in healthcare, the tradition has been to use ICD, and if we want to use registry data and electronic patient record data, then of course we have to stay with that to some extent. So the main goal of this longitudinal disease phenotype analysis is to stratify patients, not of course according to whether they have a particular disease or not, but what is the longitudinal pattern in a subgroup. So each dot here is a diagnosis code, and this is essentially the aim. And then you have something, you have a subgroup with a longitudinal pattern that you then can compare to, for example, genetic data, and you can make GWASs and so on and so forth. And this is, of course, what we would like to do. We would like to find the molecular level causes of disease, but we need to get the right side of this graph in order. What are the disease co-occurrences, and how do they hang together longitudinally, if we should understand what actually are the molecular causes that decides on disease progression terms. So we should also remember, I often show this slide in talks, that the human genome is not that gene-rich. So here we have time, and on the y-axis we have the number of genes that people thought the human genome contained. And back in 1960, the estimate was around 7 million genes, and that was before the introns were discovered. So people thought human genes more or less had the length of bacterial genes, and later it fell down to maybe a couple of 100,000. But as the human genome project progressed, I mean, we see that now we are we are close to 20,000 protein coding genes, and it's clear that many of these genes are involved, presumably in more than one disease. So pathways are overlapping and disentangling. That is, of course, also important. But again, we need some longitudinal phenotypes that can be used in this type of work. Here's another illustration from a paper we contributed to a few years ago from the NIH-funded project Illuminating the Druggable Genome. And it's quite interesting if you look at the innermost circle here, that 3% of the genome, that's targets for approved drugs, and then there are 6% in clinical trials and 50% with a lot of literature, but actually around 1/3 of the human genes are still without a lot of literature, without not many patents and so on. And it's maybe likely that many of these genes actually link to more than one phenotype, one disease. So they are harder to deal with in association studies. So a lot to discover still in the human genome functionality analysis area. So for these longitudinal analyses, we use healthcare data or registry data that stem from patient records, and we can use diagnosis, we can make drug prescription trajectories, as you will see later in the talk. I mean, our region, the Nordic region, is a good region for this type of work, because in the Nordic countries, we are not throwing health data away, at least not systematically. We still have some mess in our patient record systems and so on, but in this paper, it's not our paper, 5-year-old paper, they compared different health systems. So the yellow ones are the sort of one-payer systems that we have in the Nordic region, and you see all the Nordic countries are actually in this yellow group up here, where the electronicness is high. When you have an insurance-based model in the blue region here, there's not sort of the same incentive to keep the health data so that it can be used for longitudinal studies. But this graph is, of course, good news for also entering into Nordic collaboration, because we have data sets that actually largely match each other. But the problem is quite simple. If we look at diagnosis codes and we look at all these color-coded different disease chapters in ICD-10, we would simply like to understand the systematics in the order as a starting point. And we start on this work like 6-7 years ago and published the first paper where we used data from 6-7 million Danes, and you see inpatients, outpatients, and emergency room patients here, and you see females and males, and you see as a function of age the distribution and the density of these diagnoses in these ICD-10 chapters. And you see for the females, you see a lot of pregnancy-related codes between 20 and 40 that you're not seeing on the right side. And I mean, if you look, for example, at the brown chapter here, chapter 2, the neoplasms with cancer, you see that it kicks in earlier for females due to breast cancer here than for males, where it's dominated by prostate cancer and other cancers. And this is sort of the substrate, because this represents 6-7 million individual trajectories, and we would like to boil them down to boil these data down to those trajectories that are most frequent. And of course, also in many of the Nordic countries, you can go back. This was the sort of ICD-10 period, but you can also go back into ICD-8 in Denmark. We never used ICD-9. That's more than 40 years. So we have a lot of data that actually can almost be used to make trajectories over the entire life course, because we of course have all age groups represented in these population-wide data. And also, if you use death registry data, you can go even further back, Rock Reguant in our group, he's sort of making sort of death registry data analysis 2.0, and he tries to go back into these kind of data. I will not talk about that. In this approach that we developed some few ideas ago, the focus is not on disease co-occurrence, but it's on progression. So we're interested in finding diagnoses that actually have a direction when you talk about pairs. So when you have diagnosis number 2 here in these linear trajectories, there will be a statistical significant direction where more patients jump from diagnosis 1 to the next, and then again on to the next. And then you can sort of combine these directional pairs to longer trajectories, and then it's basically the number of patients that will limit the length of these trajectories. So actually, even with 7 million patients, you quickly run out of patients because you're looking at all diagnoses and not just a few, like in a case control study. So when you have these linear trajectories, you can also combine them into networks. And we have done a lot of that. This is a diabetes network. Here's another one with depression, with recurrent depressive disorder, very complicated before you get these green diagnoses, and also very complicated after, many different routes in these networks. Here's one with epilepsy and so on. And you can, of course, also align patients at a time of diagnosis and see what came before, for example, your first cancer diagnosis. This is from another paper that we published last year. So we essentially analyze these data in a longitudinal manner, and we can find a stratification that also can be summarized as these networks, and you can also make them sex specific. This is another paper. I think I just skipped this, but of course it's well known that the incidence and the age at onset here is different in the two sexes. And here you see a comparison of how strong the directionality when jumping from one ICD-10 chapter to another, how it compares in the two sexes, where we essentially cut the 7 million people in two halves and make a separate analysis. Many details in this that I will not go into here. This is older work, but essentially, I mean, one conclusion was from this study that females get the same diagnosis when we talk about the diagnosis that both sexes can get 4 years later than men are on average. But of course, there are exceptions from that. A lot of press stories around this paper. We actually now just published a disease trajectory browser paper in Nature Communications, where you can make your own trajectory. So you can plug in disease codes, or you can write prostate cancer, and then it will pull out these summary data from the Danish registry. So there's nothing person sensitive in this, because all these pre-computed directionalities and strength of directionalities, they are of course summaries across many patients, but you can create your own trajectories and manipulate these graphs and use them as inspiration in your work. A lot of details in that I will not go into. Here's a screenshot from an analysis of Down syndrome patients, and that's of course a diagnosis to the left, Q90 there, that you get when you are born, and you see more Alzheimer and other dementia diagnoses and so on. And there's a lot of detail on that. You can also make sex-specific trajectories now with this browser tool. So I will mention also some unpublished work here, because often with registry data and health data, people say it's very noisy, and this because it stems from healthcare. And it's also correct that there are missing diagnoses, there are wrong diagnoses, and there are maybe also over-diagnoses to some extent. And this is not from our paper. It's an interesting paper that tries to sort of describe this whole business of wrong diagnosis in healthcare data. And We think that the type of work we're doing also can be used to maybe eliminate some of the noise in the data. And I mean, if you have, for example, disease like COPD, we know that there are many examples of overdiagnosis and also underdiagnosis. And Isabella Fries in our group, she noticed some years ago that you actually, the gray diagnosis here and these short trajectories with 5 diagnoses here, that there could be many examples of very similar trajectories with COPD and without, and maybe the patients following the lower diagnosis here are just sort of simply been underdiagnosed and not been examined well enough, and you can support that also by survival curves. But in a new paper that now is in second revision, I mean, she looked in more detail at overdiagnosis, and it's quite interesting that when we look at patients who are not following a trajectory, they have a COPD diagnosis, but they are not following a trajectory. Then she noticed that those patients not following a trajectory, you see it over to the right, they actually die faster than the other COPD patients. And why is that? And then when we looked closer at it, it turns out that this group who dies faster is actually composed of 2 subgroups. One that die very fast after their COPD diagnosis, and another one that actually live longer than COPD patients do on average. And the suggestion here is that these are actually misdiagnosed and overdiagnosed patients, but because these patients have fewer comorbidities and so on. And we think these trajectories actually can be used to point at patients that might have wrong diagnosis and to some extent clean the data up. I think I skipped this one here, but how do you prove that a patient will have a wrong diagnosis? It might be hard because the patient might be dead and so on. But of course, when you go into the patient record, you can, for example, look at the lab values, and we think that some of these overdiagnosed patients with COPD, they are actually underdiagnosed for lung cancer, and that's the reason why some of them die so fast. And for example, C-reactive protein. But we look at many other lab values in the paper, so you can use that to substantiate that these patients actually had lung cancer and not COPD, as is in their registry data. So we also use now these trajectory data at the n equal to 1 level, because most of what I've been talking about here is, of course, just summary level data, but we are rarely in the Nordic countries actually using the registry data to, for example, make predictions on a single patient. We are normally just using these data for statistics. So some years ago, we went into intensive care patient data. At that time, ICU patients were not so much in focus. Now, after COVID-19, they are more in focus, and we've published a couple of papers. And this was the first one last year and another one this year. And the idea has been quite simple. For example, when you want to predict mortality, quite important when you want to triage patients in relation to ICU units. So normally you compute these survival scores based on some vital values and some vitals and some lab values and also some admission info. But in this paper, we actually try for a single patient to plug in the disease trajectory over 15 years. And then, of course, you can compare the performance of the traditional data to the right and this disease trajectory data to the left. And to our surprise, when you look at the performance when we predict mortality, we predict various types of mortalities, 30-day and 90-day and so on. I will not go into that. But if you take the orange bar here, that's the history, the disease history at admission, and you compare to the traditional blue bar here, you see we can actually make a better prediction based on the disease history than after 24 hours. That's the blue line here. So the data to the right here, that's after 24 hours. And of course, the data to the left, we have that when the patient arrives at the intensive care unit, and the historic data is actually better than what one can get out of the data after 24 hours. But the green one is when you plug it together, especially for sepsis patients. You see to the right there, the traditional blue score is not very good for sepsis patients. It's better for respiratory patients. But that's a way of using the trajectory and the longitudinal phenotype in some sense at the single patient level, and actually maybe using this kind of data at the bedside. In this paper, we make this very simple, old school neural network machine learning algorithm, but we also deal with how to explain the data and which parameters are important for the network in terms of predicting the mortality. And of course, also what such a machine learning algorithm can do is to combine the features, and we can look for interactions between the features. Actually, certain diagnoses that will lower your age. Of course, the age in the top here is very important when you want to predict ICU patient mortality. But there were some surprises in that I will not go into. But explaining these machine learning algorithms around the longitudinal phenotypes is actually also quite interesting. In a new paper that we published this year, we're not just making this 24-hour prediction after 24 hours, but we are actually making and this is Hans Christian Thorsen Meyer here, we are making a prediction every hour. So you see 72 hours here. And then Hans Christian actually explained the network every hour, so you can see which features are drawing the patient towards death and which ones towards survival every hour. That can possibly guide some of the treatment decisions. Hans Christian is an MD and has worked for many years at the ICU, but then he worked with us for 3 years and it really extended this work in a nice way using machine learning algorithms. The first approach with the simple neural network was made with Anne Laura Nielsen, and then it was extended using a more complicated machine learning algorithm. So as I said earlier, I mean, diagnosis codes is one way to approach the problem of finding longitudinal phenotypes, but the prescriptions you receive over your life course is, of course, also very important. And we are very heavily engaged in polypharmacy analysis using patient records. But here I will mention some work that we have submitted where we make prescription trajectories instead of diagnosis trajectories, and they can of course also be combined. But you see a map of Denmark here, and you see sort of the frequency of prescriptions at the level of individuals. So at some of the Danish islands, many more prescriptions than you see in other areas. But what we have done in this paper is simply to look at almost 25 years of data for prescriptions across 7.2 million people, and we have 1.1 billion prescriptions in this data sets. And like you saw with the diagnosis codes, you can make some raw statistics here. So now we are not talking about ICD or ICD-10, but ATC for the different drugs. And you see here for males to the left, you see the proportions. Not surprisingly, we have quite many prescriptions when we are babies and children, and then it levels off, and then it grows with age. And you see, for example, for the females over here to the right, that we have more prescriptions in the genitourinary system and sex hormone chapter here, the G chapter in ACT. But again, this is sort of 7.2 million individual prescription trajectories, and we would like to boil them down. And this is what we do in the paper. You see the different ATC drug classes here. And here we see different steps of statistically significant trajectories where getting one drug from one ATC group will then increase your relative risk of getting another drug from either the same ATC group or another one. And all this is just drawing those where more than 1,000 patients follow them. So actually around 7 million trajectories, but it all depends, of course, on thresholds and so forth. So we zoom in on, for example, one class of drugs, for example, and antihypertensive drugs, and then we can see how people move in the same drug group, maybe to get a prescription in the same drug group for another drug and yet another drug and so on, first line treatment, second line treatment, and so on. And of course, what we're interested in finding out whether there are patients where it would make sense to start with a third line treatment instead of starting with the first line treatment. A lot of details and a lot of possibilities for making discoveries in this area using prescriptions, because these are from the primary care sector, and 95% of the prescriptions in Denmark are coming from the primary care sector. But antihypertensives is, of course, the only one area. There are many other areas you can jump into, and this particular figure illustrates how you can take different groups with hypertensives and then you can look at their survival and, for example, compare patients who follow the guideline. For example, the red group here, they die faster than some of the other groups. I will not go into the details with it, but we think making prescription trajectories can also define patient groups that then can be compared to genetic data and other biomarker data, so that one, of course, also might find the molecular reason for these patients going from different types of drugs in the same category. And often the doctors will find the best drug, but maybe without knowing the genetics. And the idea is, of course, in personalized medicine, to jump directly to what is best for one particular patient. So what I have been talking about here in this talk is that we should maybe try to redefine phenotypes as trajectories in a more longitudinal fashion, so that we can use them to find progression biomarkers at the molecular level. So this is sort of an alternative way of stratifying patients when we look at all diseases in one go, as I have been describing. But of course, the same can be done at the prescription level, and also lab value trajectories is also something that we are working on. And instead of having this traditional case control model, this could add something to the traditional, otherwise strong epidemiology research area that we have in the Nordic countries, and handling data in a lifelong perspective is definitely of interest in a precision medicine context. And it might also be more interesting when we analyze live data. I mean, disease registries have been invented in part because one could not work on the live patient record data, but if the patient record systems actually allowed for more live data analysis, this would maybe be something that could replace the traditional register model. Nothing wrong about that, because if these had not been created, of course, epidemiology had been in trouble. So that this has definitely been a good idea. I haven't been talking much about exposures except prescriptions here, so diet. There are also socio-economic data like income and education and all that. Wearable data are coming up. In our group, we are looking now quite a bit at smart meter data that will tell you something about when you get up in the morning, at least your household, when does it start to use electricity and gas and other things. Again, these socioeconomic data can also be used to define new phenotypes, because smart meter data is also some kind of longitudinal phenotype that sort of is possibly linked to your circadian rhythms, but of course not at the level of individuals unless you live alone. So we also work with Statistic Denmark on using some of these newer data types that now by law has been sort of made compulsory to install these smart meters in houses. So these data will eventually become population-wide also. But this is the end of the talk on these longitudinal phenotypes. I'll be happy to answer questions. I have a great group here in Copenhagen. This is from a retreat, but also people outside the group have been contributing. For example, the intensive care paper, we work with the people at the intensive care unit at Rigshospitalet, but the same is the case for many of the other papers, and I will not go through these external contributions, but you need to work with clinicians who know about the unsolved problems in order to design these approaches in the best possible way. So thank you very much.
Thank you, Søren. It's unfortunately very quiet, but I'm sure there's a virtual round of applause happening around the Nordic region right now. I'll remind you that the Q&A button down at the bottom is where you should pose questions right now, and we will do the questions from the audience now and the panelists later. And the first question, Søren, from Samali Ripati is, have you correlated the antihypertensive drug trajectories with any predictive background factors?
I mean, we are doing this work together with Statistics Denmark, but in this first paper, we are not comparing to income or job categories or something like that. And I assume, Samali, that this is what you are hinting at here. We are basically just taking the prescription registry and see what is the frequent routes, and your suggestion is certainly a good one, but we have not done that.
Another question from Divya Talapragada. Could you talk a little on the utility of phenotype trajectories in the context of Mendelian randomization studies?
Yeah, I guess that if you want genetics to explain some of these longitudinal patterns, I don't think the trajectories as such change the business of making Mendelian randomization, because we are just presenting maybe some new phenotypes that can be used in Mendelian randomization studies, and then possibly find causal biomarkers for the progression patterns. But I would say that if these genetic biomarkers, for example, linked to disease trajectories where many diseases hang together, of course, making the subgroups ready is important. But that's how I look at it.
Søren, do you have a sense of how difficult or easy this is to study in other countries other than Denmark?
Yeah, I think a lot of the this type of analysis could be made, and I think also to some extent is made in other countries. One problem, and especially in the Nordic countries where we have very similar registries, of course, what is a showstopper in some countries is that the ethical authorities, they will not give you the whole registry. Because often when you use registry data for an analysis, you have to say, I want this code and this code and this code, and then I want to correlate it with this outcome and so on. That's how these applications for approval, they normally are constructed. But in this case, we got not only approval for analyzing the whole registry in one go, but also for moving it to a supercomputer setting where we actually could make the calculation. And especially for the prescription trajectories, we have more drugs than diagnoses, at least level 3 diagnoses in ICD. So there's a huge combinatorial explosion in analyzing these data. So you need to be able to move the entire registry to a supercomputer setting where you actually can do it. But in principle, I think, there's a lot of opportunity for replicating this in data from other countries in the Nordic region. And for example, the trajectory browser that we released is, of course, a starting point where you can do it yourself. You can play around with the Danish data there. Of course, there are some limitations in what you can do, but you can also use that browser, of course, just for studying Down syndrome or other trisomies or other specific diseases, and then compare to a more reduced analysis from other countries. But I do not, maybe to end this, believe that all trajectories will replicate, because if we compare to Spain, or we have some collaboration there, they eat more olive oil than we do, and of course there are exposures which are not the same, and maybe also other factors that influence your trajectory, like educational ascertainment or income and so on, will also be different. So we should not expect that all these trajectories, they are sort of the same in different areas. It also depends on whether you have a one-payer system or you have a different disease model. But of course, we hope that in certain ethnic groups that the molecular biomarkers largely will be the same.
Sulev Reisberg notes that you're generalizing the ICD-10 codes into a 3-symbol code, but sometimes an exact code would produce a stronger signal. So how do you find a good balance of disease, drug code when you're looking at trajectories?
Yeah, this is also a very good point, because as you will also see in our papers, we analyze data at the chapter level, at the block structure level, and also at level 3, but actually also in some cases at level 4. And I ultimately would be, and I entirely agree, would be best to analyze at a very fine-grained level. This is what we want in precision medicine. But as I also noted, you quickly run out of patients. So if you want to do this at level 4, you in many cases will lack patients so that you can compute what actually has a statistically significant progression patterns. But we actually have papers where we combined level 4 and level 3. In sometimes the level 4 code will say dysregulated, something and level 4 will say whether it's up or down regulated, and that's of course super important in many cases. So this is really a valid point. So what I normally also say is that analyzing data from 100 million people would be much better. But if we could, for example, combine the Nordic data, 27 million, 28 million people, and then also include the dead, we would maybe have 50 million individuals, and that would make it possible for us together in the Nordic countries to make much better analysis of this kind than just using a data set from a single country.
Sarah Bergen asks, in integrating genetic data, do you think it is more important to include specific pharmacologically relevant variants to guide prescription decisions, or genomic information to predict polygenic risk for complex diseases? Yeah, I'm not sure. I think Ross Altman recently published a paper based on UK Biobank data, where he, at least in some cases, could see that the doctors eventually did arrive at the not the dosage, because he didn't look at dosages, and we're looking a lot at dosages in our work. But he could show that that the drug that the doctors arrived at was the drug that actually made most sense in relation to the genotype, actually then without knowing it. And I think that was an interesting observation. And I think that's actually good news when we know the genotype already. Then actually implementing in healthcare the sort of decision support tools that could be used for that, I think is really realistic. And there's also some nice work in Estonia, for example, on this. So I think that is very realistic. Question from Jiang Han Zhang. The data of the ICU is interesting. Has the result been used in clinics? Because the time of any action is very tight for patients and doctors.
So we actually developed this work, and also two other papers that one has been submitted together with the ICU people at Rigshospitalet, and had joint PhD students and so on. So we are working on that, but one aspect of it that is important is that the EU made a new regulation for algorithm approval and this decision support tools. So one thing is that you have the desire to plug your algorithm into EPIC or another electronic patient record system, but it's different actually to get it in there and make legal use of it. So there's actually some processes there that we have to go into before we actually set it up and use them live in the clinic. Of course, they can be used for tests and so on. So actually trying to find out how we implement these algorithms in EPIC is something that we have started working on, but we haven't gotten any of these algorithms approved at the sort of EU approved level.
Gudmundur Einarsson says, thank you for a great talk. How do you define the different drug usage groups? Is it based on a minimum number of prescriptions, dosage, or minimum time span for usage? And then are there many parameters that define the thresholds that you mentioned for defining those groups?
Yeah, I mean, the ATC groups, of course, they are not some groups that we've defined. They've been defined by international organizations like with ICD. So this is a given. But of course, when you make these trajectories, you have to have thresholds on what you deem statistically significant and how many patients would you like to see transverse such a trajectory before you include it in your setup trajectory. So there are actually many subjective choices for this type of work, and I don't think it's so important whether you will see 1,400 or 200 different antihypertensive trajectories, because it sort of depends on these subjective choices. But of course, you can, for example, rank them according to how many patients are sort of covering each group. But that you can also explore in the browser, where you can set a threshold for the number of patients and so on, so that you, for example, also increase the relative risk, and then you will only see the strongest patterns, and then you can reduce that, and then you will see much more heterogeneity in the trajectories.
Thanks, Søren. Let's bring in the panel now. So if Kari, Lily, and Paul would turn on your cameras and your sound. Well, since Kari's the first one up, perhaps I'll ask if Kari will begin with comments and questions, and then Paul is second on my screen, and then Lily is the third one on my screen. So let's go in that order.
I am certainly very impressed with the studies that you were describing and the opportunities to follow the trajectory of diseases. And what I'm itching for doing is to have an opportunity to look at this not just in the context of genetics, but also in the context of transcriptomics and proteomics. And the beauty of adding transcriptomics and proteomics on the top of the genetics, when you begin to grind through data like this, is that the level of proteins that correlate with disease, they rise and they fall with a temporal relationship to an event, which is different from when you're working with risk algorithms based on variants in the genome that are invariant from conception to death. So I think that what you have described is basically the dream of those of us who have been working on the molecular aspects of risk of disease and progression of the same.
Thank you very much, Kari, and I completely agree. And I come from a Center for Protein Research, so actually understanding the protein complexes and the rewiring of protein complexes behind some of these disease progression patterns is, of course, in many ways our day job, or I used to be working on molecular level data only. I mean, the reason why I included this Down syndrome example is not just random. Actually, we published a paper a few years ago in Cell Systems where we tried to explain the phenotype looking at the stoichiometry of protein complexes. I mean, in a trisomy, obviously, you have more chromosome 21 proteins around, and how will that impact the phenotype? So going into that level with transcriptomic data, we just published a paper in Genomic Medicine on dysregulated transcriptomics modules in type 2 diabetes. Same thing. So I entirely agree. This is not just progression variants from genetics or risk variants. It's also these data which are closer to the now situation when you measure on proteins, and not something you were just born with.
Yeah, it's two things. One of them is it is to bridge between the genome and the clinical phenotype. Once you find the variant that's associated with risk of a disease, your task is to finding the bridge. How does the variant confer the effect on the phenotype? And number two, it is the temporal element. It is the time relationship that the proteomics add on to what you're studying. So basically, having clinical material like the one you are describing and being able to look at it at the level of the genome, at the level of the transcriptome and the proteome, it increases your capacity to shed light on pathogenesis dramatically. And the most important thing of all of this, there are thousands of variants that people have discovered that associate with risk of disease, but very few of them where they've been able to show that it affects the progression. And basically the progression is the most important aspect of all of this.
No, I agree.
Paul, we'll go to you next. I just want to say to the audience, though, feel free to pose questions to throughout this panel discussion and also to the other panelists.
Thank you. It was really a very interesting talk, Søren, and very stimulating. And there are many aspects that we'd like to think more about. And one thing is your prescription data, I think, is thrilling. And do you foresee that one can actually use that for clinical trials? That you can say that one country is having a somewhat different algorithm for how you define which drug you should use first, A or then B, etc. That you can use this your system to kind of run a very cheap clinical trial.
Yeah, I mean, one shouldn't. I mean, before you have done it, I mean, one shouldn't jump to conclusions. But I mean, I went very quickly over this survival analysis that Alejandro made. But this actually suggests that the smart doctors, which actually have understood that this patient would maybe benefit more from the third line treatment than the first line, is actually surviving better. And this analysis was corrected for sex, age, and comorbidity. So it's not just because those who follow the guidelines are actually patients which are less sick. So the Charlson comorbidity score was used to correct for sort of the disease burden in that analysis. But I think these comparisons could inspire something that then could be sort of an in silico clinical trial and then be replicated in other countries.
Exactly, because to take it from
what Paul is suggesting, which is very nice, is that all of these analyses could be looked upon as a colossal set of phase 4 clinical trials.
Yeah.
Where it was post-marketing, you could probably get better assessment of the efficacy of the drug and side effects than any phase 3 clinical trial will ever give you.
But here we are just dealing with the prescriptions. I mean, you may also know that we are analyzing millions of raw patient records where we do text mining on the notes and find the adverse drug reactions. And we're in the process of correlating that to dosage changes and to the polypharmacy situation. And I think that is actually a bit, there you get a bit closer to some of these aspects, because you look at the dosage changes, and I think it's quite sort of rough to just take drug combinations when you want to go full speed into a clinical trial. I think the dosage changes that we now have analyzed over some years, and they are not included at all. Of course, there are dosages in these prescriptions, but we are not looking at the changes, and I think that is important also.
But I want to return to genetics and obviously transcriptomics and proteomics, as Kari said. I think that is a really fantastic dimension. But how can we combine that with these data? What are the ethical obstacles, and how can we circumvent this? This is a large question, of course. But so where are you in this process?
No, but I think this trajectory business is just defining some new subgroups that you can compare genetically or at RNA-seq levels or protein levels. So I think it's maybe adding to the arguments for getting the permission to do it. But I think the principle of using genetic data to actually find causal aspects of and all that, I mean, in principle, I don't think the trajectories is changing much of that. But of course, when we submit our applications, we also need to point at benefits for the patient. And maybe if you can solve several problems in a lifelong perspective for patients, then you have an extra argument, of course. But
it is also very important, Paul, not to use the language that you used just now. We cannot circumvent the ethical objections. We have to help to reshape the ethical attitude towards attempts to discover something about the nature of disease.
I completely agree, definitely.
And also, Paul, once we have shown that using genetics in pharmacogenomics studies, as for example is going on in Estonia and so on, I mean, then we really have something to give back to the public and to the patients, right? And that kind of work will really be important, I think, also for the ethical committees to see the value of molecular biomarkers in actually helping patients.
But when you work, just thinking very practical here, you retrieve all these data from the registries, and are they anonymized, or how is that done? Because you also look into single patients at an IC units. That must be a different project.
Yeah, we have a lot of ways of working. Our analysts work with de-identified data, but often with linked data, so that you can link the disease trajectory to the ICU data from the 24 hours, high frequency data and heart rhythm and other parameters. So when our analysts work with the data, they don't work with personal identification numbers or names or anything, but we can get approval for linking the data. And in each case, we need approval for that. So that's how it's done. And then we, of course, also have worked quite a lot on secure private cloud solutions that will protect the data. Because I think it's important that data protection is not just about legal aspects, it's also about technology that can make us collaborate in new ways, so that we can combine Norwegian data and Danish data in a secure environment. So this whole aspect is also important to get that introduced, and we started working on that, like we see that in all the Nordic countries where we have a lot of focus on data security. But I think that is also an enabler that we didn't have 10, 15 years ago, right, where we could set up a secure private cloud environment and then bring all the data to one country, as we, for example, do in large diabetes projects.
That's very true. I mean, this field is definitely moving, and of course, but I think you're right that we need some good examples to convince these committees, etc., that these type of studies are really needed to take it to prediction and to take it to individual treatment, personalized medicine, right?
I will try to. I'll just ask Lily to come in, but say one thing also, that the legal working group is taking up and will be taking up many of these questions in the next year to two. And to echo Kauri's comment, there are words like that are used very often that as a science communicator editor, I recoil a little bit when I hear the words exploit or gold mine used in talks about data, personal data. Lily, would you like to make some comments and questions? And then we can, after that, let's just, it can be free for all.
Yeah, I would also just like to thank Søren for an excellent talk. And I think what makes it really elegant is the many components that you have in your hands. So first of all, just law that allows the secondary use of healthcare data for so many millions of individuals. And even though the population of Denmark is 5.8 million, you have data for 7 million. So I think that's a huge value, that you can go so much back in time, and just the longitudinal level of the data. And regarding some questions, I would also like to know, so for how many individuals do you actually have linked genetic data?
Yeah, so we better ask Kauri about that. But I mean, we work a lot together with Decode on some of these projects where we, for example, in the Danish blood donor study, have 110,000 people with genotypes, and then several 100,000 from other biobanks, like the Copenhagen Hospital Biobank. But then there's the big ISAC study, where there's also over 100,000. So there are various studies in Denmark, and I actually don't know the N, how many Danes would we have genotypes for, and it would be good to know the N actually. But then of course we need again approval to use the data in specific country contexts, and this is where I'm not sure the Danish system is more liberal there than in most other countries. I mean, the ethical committee really wants to see the arguments for this, and I think I've been speaking to the ethical committee several times, and I tried to get their focus onto this multimorbidity issue, because when you have a genotype, it's relevant for many diseases that the patient either have had or may have in the future. I mean, we now have this COVID-19, and it's essentially maybe of value for most people to have a genotype or a genome sequence in that context when we find immune defects and so on. So getting the argument through around multimorbidities and genetic data or clinical proteomic data, I think is very important, because it's a little bit old-fashioned to just work with one disease at a time. And you also see that from the pharma companies. They would like not only to reposition their drugs, but they would also like to develop drugs that actually cure several diseases at one go. And you see Novo Nordisk, for example, going into Alzheimer's and so on. So developing drugs that address more than one problem is also something that is really hot, and we need as researchers also to contribute to that, because we, at least in the academic world, we are not making many drugs. I mean, this is something the pharma industry is doing, and it's important to have that division of labor going, but of course also to have whatever we do approved by the committees.
And I have another question also regarding the longitudinal drug prescription data. So one thing that we are struggling with is that we're trying to define ineffective therapy or adverse drug events, but it's really tricky when we are looking at switching between different medications and how to define the individuals that are either not switching because they didn't get the desired effect, and the ones that switched due to side effects, for example. Do you have any good solutions for this question? And have you also been able to extract any clinical parameters like kidney function or clinical measurements that could indicate these different conditions?
Yeah, so this is also very relevant, and what I've been talking about here is mainly just registry data and a little bit of lab value data. That is also now a lab value registry in Denmark, but we have these other projects where we work with a raw patient record and where we work with all the text, and we published our first paper in 2014 on a workflow that will find adverse drug reaction mentionings in the text, and then you can correlate that to when drugs are started up and when they are terminated again. And now we are we are looking at that in sort of a polypharmacy model, which makes it even more complicated. So I just agree that we cannot get adverse drug reactions out of registries in general, because most of these are just noted in the text or hidden in some implicit way into the lab values. So, and with the kidney function, as you say, and so on, liver function, and so it's not so easy unless you have the raw patient record, and that is what we also have some approvals for. But super complicated following all these dosages, and if myself, but also especially the PhD students I lured into this, if they had known how complicated it is, then I'm not sure they would have embarked on it. But now some of it is nearer completion.
Yeah, I completely agree. We have the same challenges in Estonia, that there are excellent ICD-10 codes for said adverse events, but they're not used by the clinicians. So we've also switched to the free text records and mining these. Yeah. And it's really interesting what pops out, like that the patient didn't start taking the medication because she read about the side effects in the information sheets. And so it's
something like
free text records as well.
Yeah. No, you've also been pioneering this work, so it's I agree completely.
Thank you.
So I have a question, sir, and just for looking forward. So say that you were the director of a new hospital, and you had a lot of money. How would you kind of set up your hospital to be able to do studies like this? I mean, it's a vast possibility. Patients come in, they come out, they get a diagnosis and a treatment, etc. But usually they are not, blood is not stored, and even the pathology specimens are maybe not electronic, so it's hard to find them, etc. So how should one try to work with the directors of the hospitals to see that this might be very useful?
Yeah, super good point. And that this is also relating to what I said about live systems, that I mean, we have not worked with live patient record systems because they can hardly be used in healthcare because they are troublesome in many ways, and even less in research. And I think there's a lot of synergy between university research and maybe also company research and healthcare on trying to find out how we take the step into these live systems where we could analyze data in a new way. But I have also taken inspiration actually from what Kauri, at least Kauri was the first to mention it in this way. But there might also be others who have said it, that a hospital should in some sense be converted into a biobank. And that's another maybe structural problem that we have. We have a hospital here, then we have a registry over there, and then we have a biobank over there. But it creates a lot of barriers. And actually having a hospital or healthcare system running the biobank, so that it's much more sort of agile, and samples will not be thrown out because it's part of the operation of the hospital, rather than some remote researchers who just try to get the Nobel Prize and so on. I think there is some important lessons for us, that we've lost so many samples that could have been used to make cohorts larger and so on, because we have this unfortunate division in these sectors. So I think this idea of making hospitals into biobanks, and I hope they will also treat us occasionally, but I think that is maybe the way to go.
And
we have actually,
it is interesting. It is very interesting when you look at the current epidemic of COVID-19, that when you're dealing with a brand new disease like that, there is no difference between, or very, very little difference between clinical research and the delivery of healthcare when you're dealing with a new disease. And if you basically take away your blinders, there is a very, very large percentage of common diseases among where we are extremely thin on knowledge. And you could actually argue that the same would apply to them, that for us to be able to effectively deliver healthcare, we have to a certain extent, to approach it like it is a part of clinical research. And once you accept that, it basically makes sense to make the hospital into a living biobank. You will make research more effective, and I'm absolutely sure you will make the delivery of healthcare more effective also.
I agree completely, and the reason for asking is that we are building a new children's hospital, and I'm working with a director to make a system where everyone will be biobank when they come to the hospital. So every patient it's a biobank, as you say, Kari, and then one could define different projects, of course, connected with this, but the hospital is kind of having the ethical approval for biobanking, and then diseases will have to have specific approvals for that. I think they can be a fantastic resource, but of course one would always want more. So one thing is blood, and then it would always be nice to have urine or other tissues, but one has to start somewhere, I think. So I guess serum and EDTA will at least be a very good source to use, but it's not giving everything, of course. But if one can link that to pathology, specimens, etc., that's also a very good thing.
Yeah, no, I agree, and I hope we can convince our healthcare systems, our politicians, that that will be to the benefit of research, of patients, even industrial growth. And I mean, we are having some internal barriers that are not really good for anybody, and they are just sort of historic. I'm not saying anything wrong about biobanks, because if they hadn't been there, it's been even worse. But it's not the way to go forward in the most optimal way, just to keep that model. We need a more live model that takes these reasons that you mentioned, Paul, into account for making it differently.
Perhaps the hospital as biobank or data repository, data center is a topic for a position paper of the Nordic Society and maybe a future webinar. Are there any more comments or questions? I will mention that among our upcoming webinars, Lily Milani will speak sometime in the new year. And I think I've asked Paul Njolstad as well. If not, we should just volunteer him now, perhaps, and Ola Andreasen. And so this webinar, the recording will be posted at the Nordic Society website. And so everyone can go back and join and listen again and send it to their colleagues. The other things I wanted to just do was to just thank Søren and Kari and Lily and Paul for participating, Nico for running the show so efficiently as always, and all of our supporters, and wish everyone safe and happy holidays in very small groups.
Thank you.
Thank you very much, Hagon, for leading this so well. Thanks.